The second half this morning. So our first speaker is Chiara Piccolo from MetOffice.
Hello. So this is actually an application of adaptive methods that we look into our data assimilation system within the MetOffice. So so my presentation looked like this. First of all, I will talk about the formulation of these adaptive method within 3D VAR. 3D VAR is our simulation system. So the variational simulation system is a statistical method to estimate the atmospheric state by minimizing a cost function. And this cost function combines in an optimal way the a priori information that is usually we call the background that comes from the previous forecast cycle, with a variety of different observations. And so by minimizing this cost function, what happens is that we have what we call an optimal analysis. This optimal analysis basically depends quite strongly on the characteristics of the error covariance of the background and the observation. So the adaptation in 3D VAR, actually the formulation is basically in trying to model the correlation of this background error covariance matrix. Because this background error covariance matrix is huge, we have 10 to the 7 variables, so it's 10 to the 7 times 10 to the 7 variables that cannot even store in a computer. So what we're trying to do is modeling it. And one of the stages of modeling is trying to change the error correlations of these matrix using adaptivity. So the second bit will be the application of the application of this adaptive method in our own system, and then I'll show some results of the initial implementation that we did in our system and some of the limitation that we found. And after that, we found an improved way to remove some of these limitations. So I will go through the results of this improved implementation, and then I'll go through the summary and future work. So first, the formulation. So as has been said before in the discussion, it really depends. In an operational system, it really depends on what we are interested in and what the problem is that we want to resolve. So the problem that we faced at the time that we started this work was basically we were not good at forecasting fog or low clouds in general. And at the time there was a really big disruption in flights because we couldn't forecast fog for Heathrow during a Christmas period. So we had a huge amount of problems there. So our customers were really into pushing for getting a better structure of the boundary layer, and a lot of the problems that they keep complaining about this problem, and the problem kind of related to the background error correlation in the assimilation procedure. So what we have decided to use is a static adaptive mesh method. We don't need to use any PDE, so these methods are quite easy compared to what you do. And what they do, they relocate points. We use a fixed number of points. So we relocate points that concentrate the points in interesting area of variation of the atmospheric fields. And for us, because we were interested in low clouds and temperature inversion, so we hope that we would like to refine the mesh around strong temperature inversion or when we have stratocumulus cloud. So what we use for this static methods, we need to use interpolation to pass the analysis increment from the old mesh to the new mesh. Analysis increments are our change to the forecast state or the background state in order to get this optimal state or initial state that is the analysis from which you run your forecast. And all based on increments because it's a linear method, so it's all based on increments to the nonlinear state. And the transformation is guided by using a monitor function that is basically a diagnostic function that controls how the mesh gets distributed. And the choice of the monitor function depends on the problems and depends on the user. That's why we decided to use this particular case, or this particular method, because we can actually, depending on what we want to improve, we can change the monitor function to relocate the mesh points wherever we like. And it can be determined a priori by looking at the geometry or the physics of the atmospheric feature we want to diagnose.
So are you using observations or the background?
Background.
The background.
Because we want to have every single point. So I'll go briefly through. As I said, the background error covariance matrix is huge, so it's not possible to store. And so the only way, and is essential because it gives the weight in the assimilation system, it gives the weight to the observation or the background. And what we want really to, got the wrong button. What we really want to do is change the vertical correlations by moving the vertical level in order to concentrate this mesh point around the inversion where the stratocumulus are. So what we have decided to do is to introduce an extra transformation in the modeling on this background error covariance matrix. Because it's so big, we can store it. The only way we can deal with it is by simplifying it through modeling. And the model is done by a sequence of transformation that pass from the model state to a control variable space where we do our minimization. And what it tends to do, it tends to remove correlation in the first case between parameters by using physical relationship like geostrophic relationship, and then trying to remove vertical correlation or horizontal correlation. So what you end up with is something that is diagonal, and all the different parts are uncorrelated. So what we have decided to do is to introduce an adaptive step in this modeling of the background error covariance matrix. And what we have decided to use as a monitor function, we have decided to choose a function that depends on static stability, which strongly controls the vertical mixing of the atmosphere. So probably would also give some structure on the vertical correlation of the model variable. So the formulation we have adopted, as I said, we have this monitor function that I call M. And the first step of this transformation is to calculate this monitor function in physical space, which has an integral equal to 1. And the second step is to generate this adaptive mesh in physical space that is defined in this way as the integral between 0 to 0 of the monitor function. And the map from computational domain to physical domain is defined by this unique one-dimensional map that connects intervals of prescribed length. So finally, what we need to do is to interpolate the variable in control space, which will be generated in this zeta, and they need to be interpolated on the true levels in physical space. So the choice of the monitor function is driven mainly by a study that Andrew Lorenz did a while ago that showed that significant part of our background error correlation structure can be explained as a function of static stability. So what we have decided to do is to choose the monitor function that is a function of static stability. And also what we need to do is to regularize it in order to have a good resolution, not only around the feature that we want to diagnose, that is in this case the strong inversion, but also everywhere else. So this is how we have regularized that ensure the monitor function is positive, and it can be tuned by these factors, this constant C, and C, if C is equal to 0, basically we don't have any adaptivity in the system. So the point will be clustered, or the mesh will be clustered where the monitor function is high, and that means actually having large static stability. Another essential characteristics of this method is that it needs horizontal smoothing. As I said, for the moment it's very simple because we are doing one-dimensional adaptivity, so that means for every latitude, longitude grid point we have a new grid in the vertical. So we need a kind of consistent or coherence along the horizontal. So what we need to do is to smooth the grid. To smooth the grid, we can actually smooth instead the monitor function, and this is the kind of smoothing that we are using. If this is the monitor function, a particular grid point, we use the neighbor to smooth the monitor function, and we can iterate this procedure several times. We found out that in real system we really need to smooth the monitor function quite strongly because we have a lot of noise. So now we'll go through the application of it. So this is an example of the monitor function. This is model levels on the y-axis against longitude, and this is based on the background state, so 6-hour forecast in general. So as you can see that we can have high values of monitor function here, and that what we will expect is that the grid the levels get closer together, and also here there is a bit of orography, and so as well we have value of the monitor function, so we expect the grid gets together. And this is actually what happens. So again we have model level against longitude, and you can see for this feature we can actually have a shrinking of the levels, and here as well nearby the surface we have the levels get together. And this is an agreement with the model state that actually this is temperature. So as I said, we have our monitor function is based on static stability, and here we have potential temperature profile that actually the gradient changed quite a lot, and so we have high monitor function that implies the levels getting together. So this shows single observation tests are very useful in our system because, as I said, because this background error covariance matrix is so big, we can't really know what it looks like. So the way to diagnose how it looks like is actually putting one single observation in one height on one particular location with variance 1, and then the math tell us that is the analysis increment we get out of it will give us the structure of the background error covariance matrix. So what actually here is presenting, if I put a single observation of humidity above the temperature inversion, when I don't have any adaptivity, the model of my covariance matrix tells me that what the analysis would like to do is spreading the information across the inversion. So this is above and below the inversion. While instead, while we use adaptivity, it's much more realistic. It doesn't spread information below the inversion. And that makes sense because we don't expect error within the clouds are correlated with error below the clouds or even error at the surface. And here as well, so if you think about, if you put a potential temperature observation above the inversion, the nominal background error covariance matrix would like to spread it quite across horizontally and vertically up to the surface. While instead, using the adaptivity, we don't have that spreading down to the surface, but the error correlation is stronger just where the cloud is or where the inversion is. The other characteristic that is increase also the variance, and that would means that we will give less weight to the background but more weight to the observation. And that's very useful because one of the problems we have in this case is that we can't clearly assimilate high resolution radiosondes because this spreading is too big. and so it doesn't really fit with the error characteristic of the radiosondes. So we look at initial implementation, and there was some big limitation about that. So, but we implemented anyway for several reasons. So when we looked at the RMS error of the analysis minus the observation, we noticed that we have an improvement of the RMS errors. This is again model error against RMS errors versus SONS, so high resolution SONS profiles, and we get quite good improvement closer to the surface or on the boundary layers, what we were trying to achieve for all the variables, theta, the winds, and relative humidity. Then when we need a rigorous testing within assimilation plus forecast system, so what we want to do is not only to improve the analysis, but actually what we really want is to improve the forecast. And so, and the other things is that this stratocumulus of fog really, or stable case, happens quite a lot in winter, but not necessarily in summer. We have more convective system instead. So what we need to do is a rigorous testing that both in winter and summer. Oh, sorry, I'll skip. So that means here. So what we have done, we actually trialed different period for extended period and see the overall performance of the system when we introduce adaptivity. And what we noticed is basically that the 2 meters temperature has improved, the forecast of 2 meters temperature has improved. So what you get here, if this is forecast minus observation RMS errors as a function of forecast lead time. So we have improved the analysis system, and this is still has some benefit over the forecast range up to t plus 15 hours. It's not massive, but it's basically was nearby the surface. And that's mainly because, if I go backward, what the grid tends to do is tends to clusters more mesh points nearby the surface. And so the error correlation of the background is smaller, and that means that we have higher variance for the background. That means we will give less weight to the background but more weight to the observation. So we will have a better use of the observation nearby the surface, and that's what has implied the benefit in the assimilation, the forecast nearby the surface. But we had problems with it, basically because the monitor function is based on the background state. That means the previous 6-hour forecast. And so that means this is gives you an example of the limitation. Here we have 2 different cases in UK where we have SONS, so observational in red, where we have a strong inversion. And then we have in pink the background that doesn't have the inversion at all. And then we have the case where we use the standard grid or the nominal grid in black and adapted grid in blue. And as you see, there is no real, they don't see the inversion, they don't pick up the inversion at all. And this is actually even more complicated because we have more than one inversion. And basically what it is, our adaptivity is based on this pink line. So if the pink line or the background state doesn't have an inversion, or has it located in the wrong place, it does adapt in the wrong place. And so it changed the error correlations in the wrong place, and it doesn't change the position of it. It just changed the correlation of the background error. So basically, we don't get any benefit from it. And that was one of the biggest limitations we had at the beginning of the first implementation. So we're trying to improve that results, and the way we did was, first of all, we use a more appropriate normalization factor that takes into account the fact that the monitor function, we normalize it after the monitor function was smooth and regularized. But more importantly, what we decided to do is trying to do it, the recalculation of the grid in an iterative way. So instead of doing it using the background state, the forecast, we were trying to use an updated version of the forecast. So that meant doing a bit of an assimilation for 10 iterations, so being exposed to the observation. So we have an updated background state or first guess analysis, then use our adaptive tool based on that and iterate for other 10 iterations, and then and calculate the grid, and then recalculate the grid on the new assimilation stage that we get from stage 2. So basically what we do, we calculate the grid twice when we update the background state or the forecast. So we looked at a particular case that was the 3rd of January of last year, and this is an image, we pick up an image to test this technique. This is the Meteosat second generation image at 3.9 micron over UK, and basically what it shows is the emitted radiation from the surface and cloud tops, and the resolution of these instruments is basically 3 kilometers. So white areas here shows cold temperature, that means high clouds, while dark area like this one shows no clouds. And you can see the contrast between here, for example, between sea and land. And what you can see basically that is a very good case study, because we have different clouds at different levels. And basically this gray area is low cloud. So here, for example, we have high clouds or on top of low clouds. So it's a good way if we can try to see different layers of clouds and if the system can adapt to that. So first of all, I compare the previous implementation where we had a lot of adaptation. This is again the monitor function of model levels against latitude in this case. And there was a high monitor function really close to the surface. As you can see, the results, the grid moves little and basically nearby the surface. Here is a zoom of this area. While instead, if we use this new normalization techniques, we managed to span better the atmosphere, so to capture more structure and to capture those different levels of clouds, the high clouds and the low clouds, like these levels here and this bit. And as you can see, as a result, also the cross-section of the grid does change quite a lot, and it picks up these different levels where the cloud is, so up here or there. So we get the mesh refinement where the monitor function is high. Well, the second implementation was about this iterative calculation of the grid. So this is the case where this is the monitor function again as a function of latitude. This is the case where we use the background state, so the previous forecast. And as you can see, I've highlighted some parts to have a look at the differences. Well, this panel is where we have done the assimilation for 10 iterations, so we kind of improved our knowledge, our a priori knowledge of the atmosphere by using the observation. And so as you can see, there are some changes in the monitor function. For example, here's this blob that we liked, in this case, we like to put lots of levels here. Actually, after the exposure to the observation, it says, no, actually, we don't need the levels here. And then we recalculate we do another iteration, and we recalculate the monitor function and the grid based again on this new update kind of guess. And again, we see that it changes quite a lot. The squash is much more localized, and that means that because we don't want to refine it, what actually we're saying we want to still give a good we still have good information from the background, but we want to localize more where we want to adapt. So then we tested it in a more statistical sense. So we look again at the RMS error of the analysis minus the observation for potential temperature in both cases. And one case here is where we don't do any cycling. So, in our system we have variational simulation, and then you have the forecast, and then the forecast feedback again in another variational assimilation, and so on and so forth. So in this process, you actually improve the analysis. That means improve the forecast, that you have an improved forecast in the assimilation, and so it feeds into itself. And so that's what I'm showing, the difference between these two panels. So when I adapt, starting from the same background state compared to the first implementation, that was this black line, we do have improvement from the normalization, the beta normalization, and the cycling of the grid in both cases. But when we cycle, as I said, we do get a much better improvement, basically because at every cycle we improve the background state. And so we adapt to the background state, or a version of the background state, and so it gets better. And again, in order to implement it operationally, what we need to be sure that we don't degrade the performance in either area or in other time, or for example in summer. So again, we need an extensive trialing of big period of trialing. And what we tend to do, we look at what we call Duquesne indexing. The Duquesne index is really a verification against WMO observations at particular location for particular parameters. This has been designed internationally, what parameters or what observation to use. And so what we tend to do is looking at this particular verification parameters, and that basically are for a limited area model, like UK model in this case, visibility, precipitation, cloud amount, cloud base height, temperature 2 meters, and wind at 10 meters. So what we can notice that if we have beneficial in almost all the fields for both periods, and overall we have a benefit of it, so we decided to implement it. This number seems small, but actually compared to our role, what we forecast our benefit in a year is, this is a 2/3 of what we forecast for UK model. So it was quite a good achievement in that. Do I do it with time? So the other thing we look at is, so this adaptivity, where is the contributions coming from? And so just go quickly, we looked at radiosondes again, because is the best information we get for our vertical structure. And here we have the statistics of observation minus background, and negative value means improvement for different variable. And basically what you notice that we see noise in the RMS errors versus sondes. There is not big, huge improvement. But again, what you get a very good improvement when you do observation minus analysis for radiosondes. And then also we looked at the other type of observation that the system sees, and in black we have observation minus background, while in white we have observation minus analysis. And we have aircraft measurements and surface measurements here. And then we have severe measurements here. There is an infrared instrument, or MSG. And then we have ground GPS and sat winds. So what you can notice that for aircraft measure, we have an improvement both in the statistics of the comparison with the background minus observation and background observation minus analysis. While in the surface, the signal is not that clear. Actually, we have a big degradation in surface temperature, and that makes sense because in the previous implementation, if you remember, the monitor function was really picking at the surface. So what it was doing is putting a lot of levels at the surface. Well, now we're actually, because we have a fixed number of levels, what we can do is we can only redistribute the levels. We don't add or remove levels. So the levels that were at the surface needed to be distributed also in the rest of the atmosphere. And so we have removed levels from the surface, and that's why the degradation compared to the previous implementation. Instead, with satellite data, we have good results. These two channels are humidity channels, while these three are windows channels, so basically are picking lower down in the atmosphere, and we have good results for both of them. And also ground GPS is basically integrating water vapor content, and so we're actually improving our background error characteristic when is compared to this kind of measurements. But we don't have a great impact on sat winds, and that makes sense because our monitor function is based on static stability, that is a physics variables and not a dynamical variables. So it would be a secondary effect on winds. And this is what the problem was about. So this is my final slide. So if you remember well, in the previous implementation, we had very strong inversion. In red the observation, and we couldn't really get any better by using the adaptivity because the background didn't have that inversion in it. So with the iteration, what we have achieved instead is, as you can see here, the background has a better inversion. So we are actually getting better to represent the vertical, the vertical inversion of temperature. We also have improved humidity and the lower troposphere. In the upper troposphere, we have lots of problems, but that's really related to the quality control of the system. But still, we have a major limitation, so that is that this adaptivity, although it's done only in the vertical, it does have an effect on the horizontal because we are doing the horizontal smoothing. But the horizontal error correlation of the background depends on how we define it in our system. And at the moment, they're really long, of 100 kilometers, although we were trying to resolve really local effect. So this actually wash out because we have such a long length scales, wash out the information the adaptivity is trying to get. So we hope that by improving the length scales of our background error, we might be able to use adaptivity more strongly. So in summary, so we have done two operational implementation. The first one was the one that was done in 2010 and has mainly have an impact into meters temperature. And the second one that involved the recalculation of the grid was implemented last year. And as I said, the main limitation is due to having these long horizontal length scales that are fixed at every vertical mode. So this wash out all the local effect that adaptation would do. And so with more realistic length scales, we might be able to detect more local phenomena. And in the future, what we are really interested in to extend this 1D transformation in 3D. And work is already in progress, and Chris Budd is going to talk tomorrow about it in his Monjambert based moving mesh method. And basically that's what we would like to go towards to. So that's it. Thank you very much for your attention.
To clarify one detail for me, so do you end up with an analysis on the adapted mesh at the end, or just on the original?
No, the analysis is on the original mesh. So we don't actually, maybe there is a confusion, we don't change the mesh in terms of the analysis procedure. We change the mesh in terms of the background error correlation. So what we change the background error correlation that are seen when we compare it with the observation. But then the analysis is still on the fixed grid.
And would it make any sense to do the analysis on the adaptive grid as a post-processing step?
I think it would be very complicated.
Mm-hmm. And do you have a sort of view for how this could be incorporated, sort of ideas from this could be incorporated into a 4D VAR?
Oh, 4D VAR, no, well, 4D VAR, it's doable. Well, actually, it works with 4D var as well. It's no problem between 3D var, 4D var, because this is about, again, the background error correlation at the beginning, and then you evolve 4D var. What it does, evolve the background error covariance in time, and then so so at the beginning is adapting it as adapted correlation that will be evolved in time, but it's still static. In a way, the model,
Yeah.
the
But would that
Jacobian will move it forward in time.
But would that evolution occur on the adapted mesh? Or would you go back to the...
Now we'll be back in the nominal mesh, but the correlation are already flow dependent, are already distorted. So what we use the adaptivity to distort the correlation, not the mesh. So the calculation is all done on the. It's only the background errors that changes.
Any other questions about that talk? Okay, well, let's thank Chiara again.